You probably have crossed one several times in your life, but have you paused to consider how they were built? They connect us, different cultures, locations, and people, and make traversing the otherwise difficult terrains or obstacles easier. They have been the reason for iconic movie scenes, economic growth of several cities, and major tourist attractions. Some of the most iconic landmarks in the world, like the Golden Gate Bridge and the Brooklyn Bridges, have played major roles in society, not only as means to connect people over rivers, highways, and even oceans, but also bring cultures together. They are also a symbol of human ambition and engineering skill. If you have ever wondered how these structures are built, in this video we will explore in some detail the fascinating process, from the sketch, design to building. Remember to subscribe so you don't miss out on more marvels we will continue to cover in our YouTube channel. So this is how bridges are built. The story of bridges spans centuries, but the early forms of bridges were simple. They were made from easily accessible materials early humans could find. These were wooden logs, vine, dirt, and stone. Obviously, with the limited materials, the bridges could only cover short distances, like small streams and valleys, not the larger bodies of water and rougher terrains they can span over in modern times. The Romans were master builders, evidenced by the many structures they created that still stand today, like the Roman aqueducts and Colosseum. Romans contributed to the advancement of bridge building in two major ways. First, the invention of concrete mix with used volcanic ash to make mortar. These allowed for larger and more sturdy bridges that could span greater distances. Secondly, they discovered structures could be built with arches, so that loads would be supported by those arches. Applied to bridge building, it means bridges could be lighter, but still carry heavier loads than before. Many of their structures, like the Pont de Gard in France, still stand today. After the Romans, advancements in bridge building somewhat stagnated, unless you consider the innovation of rope suspension bridges, which were more common in South and Central America. We do not see major innovation in bridge building until the Industrial Revolution, when steel and reinforced concrete opened new possibilities, giving rise to engineering marvels like the Brooklyn Bridge and the Forth Bridge. We could say that the era of the modern bridges starts in 1779, when the first iron bridge was successfully built over the River Severn. This was a turning point, because after this, iron came to be widely used in the construction of bridges and even aqueducts and buildings. Let's step back to the beginning of the 18th century, in the nearby village of Coalbrookdale, where Abraham Darby pioneered the smelting of iron using coke. Then, Abraham Darby III was responsible for the ironwork for the bridge that still stands today, using the same techniques developed by his grandfather. The bridge was so successful that it gave its name to the spectacular wooded valley which surrounds it, now recognized as the Iron Bridge Gorge World Heritage Site. So, how do engineers begin to construct bridges? Well, they have to answer a few questions. The most important obviously is, where will the bridge be located? What kind of traffic will the bridge carry? Pedestrian, cyclist, rail, vehicle, or a combination? It is also important to choose the bridge span, environment which the bridge will be located, so questions about the site conditions have to be answered. Questions about future developments in the area, questions about funding and budget constraints have to be answered as well. Obviously there are many more questions, but let's move on to the types of bridges, because this does affect the way the construction will be done. There are 5 main types. Beam bridges are the simplest and ideal for short distances. Arch bridges have curved designs which distribute weight efficiently. Truss bridges, one of the more lightweight ones, are still exceptionally strong due to the use of triangular frames. Triangles are strongest shape because they distribute forces evenly across all 3 sides. Suspension bridges are perfect for long spans. They work because they use massive cables that are anchored at both ends and pass over tall towers. This design efficiently distributes the weight and forces, allowing for long spans and substantial load-bearing capacity. And cable-stayed bridges are a solution for medium to long spans crossings. Each type serves a unique purpose, shaped by terrain, traffic, and technology. As we briefly hinted at before, building a bridge begins long before construction. Engineers analyze the site to determine soil stability for depth to water levels, wind speeds to seismic activity. They calculate every potential force a bridge must withstand, such as the weight of the bridge itself, the vehicles that will cross it, and environmental pressures like wind, snow, and earthquakes. Modern bridge designs are modeled digitally using advanced CAD software, simulating stresses, vibrations, and failures before any materials are used. These simulations help engineers determine the bridge's behavior under different conditions that may include the weather and loadings it is subjected to. It's not just engineering, It's also logistics, securing permits, managing costs, and minimizing environmental impact. Every line on a blueprint represents hours of research, safety reviews, and precision planning. Bridges are only as strong as the materials they're made from and are commonly built using a combination of steel, concrete, stone, and wood. The most common materials used are steel and concrete. Steel is favored for its flexibility, strength under tension, and durability, making it ideal for the main structure, while concrete is used for the deck and foundation due to its strength under compression and durability. Some older bridges, especially arch bridges that have stood for hundreds or thousands of years, have used stone. Wood still has its place in smaller spans and temporary structures. It has limited strength and durability, however. It's relatively inexpensive. But none of it matters without a strong foundation. It can be argued that the foundation is the most critical part of the bridge because it has to support the whole weight of the bridge and traffic loads. The type of foundation chosen for the bridge depends on the type of the bridge and soil conditions. The foundation can be deep or shallow. Construction works must clear and level the area which the bridge will be built of any obstructions, and level the area to place the foundation. Over soft soil or water, engineers use deep foundations like piles or caissons, massive columns that reach down to stable ground or bedrock. Shallow foundations rely on soil with large bearing capacities, and the load of the bridge is distributed over large areas, instead of deep into the ground or bedrock, as would be the case with deep foundations. In some cases, entire foundations are built underwater using pressurized chambers or cofferdams. These present challenges such as pressure and corrosion, that is, if water cannot be extracted or diverted during the construction process. Piles are driven into the ground, displacing water. If water cannot be displaced, cofferdams come in. They are built temporarily to allow for worker to have a dry space to work. It's an enormous task, but it ensures everything above remains stable, no matter what happens below. Once the foundation is secure, construction moves upward. First, the substructure is built: piers, columns, and abutments that support the bridge. Piers are built by drilling into the riverbed, installing rebars the covering with concrete. Then the cofferdam is constructed to keep the water out. This allows workers to build the caisson, which is a box-like structure sunk to the ground by using its own weight or buoyancy. This is followed by excavation and then backfilling, using concrete and other materials to provide stability once the desired depth is reached. While cofferdams are temporary structures, caissons are permanent and act as the foundation of the bridge. Reinforcements are used to provide necessary support. The formwork for the pier must withstand the pressure of wet concrete and maintain the desired shape of the pier. Sometimes scaffolding is used to provide access for workers. Concrete is poured into the formwork so that it dries properly without air pockets. After the concrete is poured, it needs to be cured so that it reaches the desired strength. Then comes the superstructure, the visible part of the bridge, including the deck, beams, arches, or cables. In many modern projects, large sections are prefabricated off-site, then transported and installed using cranes or barges. This modular approach reduces disruption, improves safety, and speeds up timelines. Once the deck is laid, crews add pavement, guardrails, lighting, and expansion joints. What started as a sketch is now a structure that can bear thousands of tons, and traffic from millions of vehicles. Before any bridge opens to the public, it undergoes rigorous testing. Engineers simulate extreme weight loads, sometimes using trucks filled with concrete or water. Wind tunnel testing helps predict how the bridge behaves in storms or strong gusts. Seismic dampers are installed in earthquake zones to absorb shock. And once opened, many modern bridges continue to be monitored in real time using embedded sensors. These smart systems alert engineers to any structural changes, ensuring long-term safety and performance. The future of bridges is smarter, faster, and more sustainable. Engineers are experimenting with self-healing concrete, carbon fiber reinforcements, and 3D printed bridge components. Drones and robots now inspect hard-to-reach areas, reducing risk and improving accuracy. Some smart bridges already monitor traffic, temperature, humidity, and structural stress, automatically reporting data to engineers in real time. As cities grow and technology advances, bridges are evolving from static structures into intelligent infrastructure. Bridges are more than pathways. They are monuments to human achievement. They blend science, art, and ingenuity, turning raw materials into structures that span rivers, connect cities, and stand for generations. So the next time you cross a bridge, take a moment to appreciate the engineering beneath your wheels, and the incredible journey it took to get there. If you enjoyed this journey into the world of bridges, Be sure to subscribe for more engineering deep dives. And let us know in the comments. What's your favorite bridge in the world?